Okay, so the objective is to understand what exists and for all mean in set. Now, I think I've done videos on this before, but it's a delicate matter, and so it's worth revisiting. And also, we're going to get a new perspective on there exists using one of the Kierkegaard principles. Now, I'm going to understand what's going on, or I'm going to try and explain what's going on with these quantifiers in sets in a pointwise fashion. But I'm really interested in kind of when arrows are in other arrows, in particular, when functions are in monics in set. So this is a very useful result. It says that for an arrow f from A to B and a subobject s of B, we have that f is in S if and only if for every point in A we have fa is in S. So let's prove this. Well, let's just see a picture for a start. Here's a nice picture of it. So we're saying that to say that this function f is in this subobject S is as to say that for every point of the domain of this function, doing f on that point will give us a point that's contained in S. Okay, so let's assume that f is in S. Well, then there exists a k such that f equals sk, and then that implies that fa equals ska for every point little a of A. So that means that the left statement implies the right statement. Now, assume the right statement. Now, for every point of A, we know that fa is in S. Well, we're assuming that. And so let's let ia be the point of zeta that is such that fa equals S after ia. So we're talking about this kind of thing. We have a fa here, we know that's in S, so there's got to exist this ia arrow. This point of zeta. Now we define an arrow or a function k from A to zeta such that for every point of A, we have that ka equals ia. So now for every point of A, we've got that fa equals sia, and doing the substitution, that's equal to ska. And so since we're working in sets, if two arrows agree on all the points, then they're the same. So that means that f is equal to sk. So then f is in S. So that means that the right statement implies the left statement, and the theorem's proved. So given that, that means if we can understand how there exists and for all work in terms of points, then we can understand them in general. So let's consider a formula, theta. Well, suppose we have some arrow m from a times b to omega, and so we'll write that theta is m of x comma y, where x is a variable in a and y is a variable in b, and we have this arrow, a general arrow into a, and we're interested in this, for this theorem, we're really talking about, we're interested in this problem is when is c in this extension of there exists a y such that theta when is c in this extension? Well, this happens if and only if, this is according to theorem 18.1, remark 6 of it, this happens if and only if there exists a epoch from some object zeta into t and an arrow r from zeta to b such that cs comma r is in this extension of theta over x and y. So let's try and understand this. So when t is equal to 1, the only way we can have an epoch into t, well, so we're going to consider as t equals 1 case because we're interested in the point case, and the only way we can have an epoch into t, assuming we're dealing with a non-trivial topos, is that we must have that this zeta which we pick out is not the initial object, because we need there to be an epoch from zeta to t, and we already know that that arrow from the initial object to the terminal object is mono, because in fact for any x if we have well, at least in this case, we automatically have MF equals mg. But in a topos, the only arrow into an initial object is one that comes from an initial object. So it's all fine. So yeah, that's a monomorphism. But we know it can't be an epimorphism. We know that this arrow from 0 to 1 can't be an epimorphism. Why? Because in a topos, anything that's a monomorphism and an epimorphism is a isomorphism. And since it's non-trivial, we're assuming that it's the initial object and terminal object are not isomorphic to each other. So there's no way that this zeta could be the initial object, because we require it to have an epimorphism into our terminal object. And that'll turn out to be important. Now, we need there to exist this S from zeta to t, so that has to be exclamation mark zeta. It's the only choice. And so this star thing holds if and only if there exists an arrow R from zeta to B such that C after exclamation mark zeta comma R is in this extension of theta over x and y. Now this holds if and only if doing the interpretation of theta, which is m, after C exclamation mark zeta comma R gives true. Now, when there exists such a zeta, it turns out that this statement can be simplified, because we might as well just talk about points, because if this works when zeta is the terminal object, then of course it's satisfied. And it turns out that if it's satisfied, it'll work for when zeta is the terminal object. Why? Well, suppose this works for some zeta, and suppose working in set, and we know that zeta is not the initial object, so it has to have a point q. And so if this statement green star holds, statement up here, then we have that m of C exclamation mark zeta comma R after q equals T exclamation mark zeta q. And so there exists this point RQ of M such that C comma RQ is in this extension of theta over x and y. And so we can simplify star just to say, the simplified condition is just that when we have a point, we'll have a point C in this extension of there exists y such that theta, when working in set, and C is a point, that happens if and only if there exists a point R dash of B such that C r dash is in this extension, which makes a lot of sense, right? That there exists this y, x is such that there exists this y with theta done, is similar to saying that, we can find a point C and a point C of A and a point R dash of B, which satisfy this theta, okay? Now, we can also have a go at applying the other one, which is for Forall. So we have the same setup as before. And this time, C is going to be in this extension of Forall y theta, if and only if for every arrow S from zeta to t, and for every arrow R from zeta to t, we have C S R is in the extension of theta over x and y. So if we suppose that t is a terminal object again, this occurs if and only if for all arrows R from any zeta to b, we have that C exclamation mark zeta comma R is in this extension of theta over x's and y's. And I claim that this actually happens if and only if C exclamation mark B comma 1b is in this extension of theta over the x's and y's. So it's basically, I think, if you take this case and set R equal to 1b, and that case holds true, that will imply the others. But my proof of this is a little bit, it's not really using this approach. It's using the kind of pointwise version of this type of results you get by approaching this with the Mitchell-Benebaugh language. So here it goes. C is in this extension of for all y theta, if and only if doing the interpretation of this thing, this term here, after C gives true, if and only if for all B transpose M, so transpose M is interpretation of phi transposed, okay? So for all B after transpose M after C gives true, and that happens if and only, since this is a classifying arrow of a name of TB, this happens if and only if transpose of M after C is in TB. Sorry, is in the name of TB. Now, name of TB is TB after P2 all transposed, and we can rewrite transpose M after C as transpose of M after C times 1B. So this is equivalent to saying that TB after P2 equals M after C times 1B. And there's an arrow, so we have this arrow P2 going from 1 times B to B. It's an isomorphism. Its inverse is exclamation mark B comma 1B, so we can do that, like we can put that in here. And then we can go this way around the diagram, so we get that this is equivalent to saying that TB is equal to M after C P1 comma P2 after exclamation mark B comma 1B, and that's equal to TB. And we can simplify this to m after c exclamation mark b comma 1b. So this, our condition then basically says that c is going to be in this extension at the top here if and only if c exclamation mark b comma 1b is in the classifying arrow of m, which is the extension of theta over x and y. And that is this result here. So there we have it.